This is chapter 6 in the course structure. Let's see, and it's referred to as thermochemistry. This essentially is a topic that's derived out of the laws of thermodynamics. Which is the study of energy changes in chemical and physical process. So one of the first things we have to deal with is, well, what is energy? Can anybody tell me what the color energy is? What does it taste like? See, this is the abstract nature of what we're about to study. Do you believe in energy? Of course. Yeah, everybody is aware of, well, I've lost all my energy there. I got real energetic. And the concept of energy is to provide a higher level of performance. And so we talk about energy in a couple of contexts. We talk about energy in a practical context and then a scientific context. From a practical issue, just to name a few, mechanical energy, electrical energy, nuclear energy, and so forth like that. So if people are discussing the applications of energy in a more practical applied context, then they would probably use it in terms of these this terminology. Now from a scientific standpoint, I'll move that down a little bit so we get some. We find energy is actually divided into three areas: kinetic, potential, and what we call internal energy. Some of you already know what kinetic and potential are, but you may not be familiar with the term internal energy. Well, kinetic energy is the energy of motion. When something is in motion relative to a starting point and a target destination is giving off kinetic energy. Potential energy is stored energy, a positional energy is what I call it. If we have an object on an elevated platform at some height above the ground, this would have a potential energy on top of the stage, and if this were to drop to the lower level, that would be potential energy, say 2. And potential energy 2, of course, is less than potential energy 1. Now, one element that connects potential energy and kinetic energy is as the object falls through the from the start to the end, it gives off kinetic energy. So kinetic energy is released and you have a lower potential energy. So really, potential energy plus kinetic energy gives you total energy, and then it falls down here, loses some of the kinetic energy, and its total energy is less. That's just kind of a scientific explanation of what's going on. Now, we will not study potential and kinetic energy in chemical context. What we are interested in is this third one, internal energy. So you'll note internal energy, and the symbology is a delta E subscript I for internal energy. Well, straight away, the definition. This is energy content of a system due to its chemical structure and state of existence. So two factors, chemical structure and state of existence, go into what we refer to as the internal energy factors associated with the reactions that we're going to be doing. To illustrate this, let's talk about state of existence. Of course, that is referring to solids, liquid, or gas state. That's the common, what's the state of existence, solid, liquid, or gas. And so we can say that if we were talking about ice, say a block of ice, versus a quantity of water, liquid, and gas phase steam, this would be solid, liquid, of course gas. It doesn't take a lot of insight to understand that the ice is ice because it has a low level of internal energy, or we take energy out, we freeze it, okay? So that the particles come closer together and they bind however they're supposed to bind, and a solid is generated. So in order of increasing energies, we find the ice has the lowest energy, and then at some point in the transition from ice to the water, we find it runs into liquid. Now, we haven't changed the substance. It's still H2O in the context of what we're talking about, but it has the ability to take on and lose energy to achieve certain states of existence. And so here is the state of existence as a liquid is a higher energy level than it is if it's in the solid state. And of course, that is then transitions into a gas phase water or steam or vapor, and we find that this has the highest level of internal energy. So it is the internal content. Now, we can't touch it, feel it, see it, taste it. It has no visible characteristic colors or anything, but we know in a general sense that, well, if I'm going to have ice, it's going to have the energy taken out, and the ice is going to be at a low energy, and then water is going to be between the solid and the steam, the ice and the steam. So this is kind of an intuitive deduction relative to the energy contents. Okay, state of existence. Now, when we talk about the chemical structure, on the other hand, that involves, of course, the bonds, the elements that are in the structure, the molecular geometry and dimensional structure, three-dimensional structure of the substance. Now, to clarify this, let's take a reaction, hydrogen. I'm going to draw it in Lewis structure. Hydrogen is H2, like this, and then oxygen actually is a double bond like that. And then what are we going to do? Make water out of this. So H. And this is, and you'll learn about these later on in the semester, how to draw these structures. Well, what can you say about the visual structural image that you're looking at? Fundamentally, none of them are the same. Okay? Now this is linear and linear, but it also contains some other stuff in it. But the point is, this has an energy, what we call an energy content for hydrogen, an energy content, a potential positional energy. Energy content for the O2, H2, and then we have an energy content for H2O, such that they're different. And this is what we talk about the energy. These rearrange themselves and wind up in this bent angular looking structure for water, and that angle plus whatever's in the structure and the bond energies and what have you go into the internal energy content due to structure of the water. Well, this one has an internal energy content, and this one too, because it has structure and certain kind of bond. So this is what we're talking about when we're talking about chemical structure. Now, when we take the difference in the energy of the products and the energy of the reactants, then what we get is the heat of reaction. Change in energy of the reaction is the energy of the products, which would whatever they go to, minus energy of the reactants gives heat of reaction. And in essence, that's what we're trying to look at in terms of thermochemistry. Now, what we're looking for at say an answer to a change of energy, that answer will embody both the structural and state concepts. So you go from reactants with state and structure different than the products with state and structure. These are different. And the essence of that differential is the heat of reaction. So what we're trying to do is teach you what is energy, what is it, how does it relate to chemical equations, how do we apply this to chemical reactions and the changes of energy that they experience. And the experimental aspect of this, I'll show you a demo probably next class on how it is actually measured in the laboratory. Energy, by definition, is the capacity to do work. Our physics friends then define work as a force acting through a distance. Now, we're not going to work problems in this context. What I'm trying to show you here to illustrate the issue is the units of energy. You can title this units of energy. Now, force from Newton's second law is mass times acceleration. And then we replace distance. And so work now is dependent on mass, the acceleration of the body, and the distance it will move. Well, when we apply the units for this, work units, mass in the SI system, SI units, will give us kilograms times acceleration is a change in velocity with respect to time, which ultimately works out to meters per second squared, and then distance is in meters. So those are the units of each one of the terms in the definition of work. Well, this combines to kilogram meters squared over second squared, a complex unit that's cumbersome at best to work with in, say, working through chemistry problems and trying to write out the units associated with it. So in the distant past, scientists recognized this as a problem. So they redefined this as the joule. So this is, a joule is derived, or the heat energy called joules, is derived out of the definition of work, which is force times distance expanded through mass acceleration distance and putting in the SI units, and we get the complex, and it's simply the value of joules. Now with this we've heard of. The other units for energy is the scientific calorie. It's usually given a lowercase c. Joules is a lowercase j, like that. Now, calories is a measured standard in that it represents the amount of heat needed to make a physical change. Now, this is what ultimately specific or scientific calorie is. 1 calorie, and it's a lowercase c, is the amount of energy needed to raise the temperature of 1 gram of pure water, 1 degree Celsius. That is the technical textbook definition of the scientific calorie. Now, don't mix this up with the nutritional calorie. A nutritional calorie is a kilocalorie, 1,000 of the scientific calories. So what we'll be working with back and forth between joules and calories is the scientific calories relationship to the joules. And what that is much more than a conversion factor. 1 calorie, scientific, is 4.184 joules. And so now our concept is just really broken down to the simplicity of this conversion factor. So you'll work out a problem and you'll either come out in joules or calories. And depending on what the problem's asking you for, you'll either leave it in the existing set of units or convert to some other kind, to the other dimension of units, like that. Okay. Which you probably are well aware of at this point in your scientific studies. Energy cannot be created nor destroyed. It can be changed in form, but not created or destroyed. And what this ultimately boils down to is the total energy of a universal system equals 0. That is the energy total, change in energy total, is the sum of all your changes in energy internal, and all that is essentially equal to 0, is what it boils down to. All this ultimately, we can put it in one other context, the change in total energy is equal to change in internal energy plus change in kinetic energy and sum of change in potential energy. So this kind of sums up the big pictures, and we're either changing in pieces and parts. Now, we're going to be working primarily with the internal energy here, and so it's not going to always show up a 0 or something. There's a solution that I use for certain kinds of energy problems where you set everything equal to 0, but I will show you how that works in a few minutes. But what our interest is right here. What is the change in internal energy for the system we're studying? And that is the chemical reactions. So when we talk about energy change in chemical reactions, we refer to this in a generalization, energy changes in thermochemical reactions. Thermochemical reactions are of two kinds, exothermic and endothermic type of reactions, where the exothermic exit means energy is liberated. Endothermic is, of course, the absorption of energy by the system being considered. Now, in order to truly understand the use of the terminology, we need to look at what we call the system and surroundings concept. I think I've used this before. This is a T-table. This little cross-haired looking thing like this. On the left, what we're going to do is put the system up here, and on the right, we're surroundings. Now, when we talk about systems, this is the object of interest. That is the chemical reaction. And the surroundings is everything else. Okay? So what we're looking at is, say, a reaction. That includes both the reactant side and the product side, all in one category. So we can say reaction in this circle right here. Now, in the process of that reaction, the reaction is either going to be losing energy or gaining energy. So in this reaction, we can draw a little squiggly line indicating, say, that's a loss of energy. From the system, which we call exothermic, but we don't specify what I'm about to write, but it is supposed to be understood. Exothermic with respect to the system. So the point here is a loss of energy from the reaction system, But if you look at where the energy is going, it's going over into the surroundings. So it's endothermic to the surroundings. So when we use the term exothermic, that's why I say it is to be noted to be from the system, not the surroundings, because the surroundings is doing opposite what the system is doing. And of course, if you have the same consideration down here for a reaction where energy is coming into the system from the surrounding, this would be gain of energy by the system. And this is referred to endothermic with respect to the system. Because you have to keep that in the back of your mind intuitively, because it is exothermic to the surroundings. But in the discussion, we want to emphasize that it is taking energy into whatever the reaction is that we're simply looking at. Okay. Symbology of thermochemical systems. So we need to write an equation that illustrates an exothermic reaction, and then one that shows an endothermic reaction. Now the way this is done, I'll choose a reaction 3H2 as a gas plus N nitrogen, molecular nitrogen gas, make that a little better. Nitrogen gas goes to ammonia gas. And the way we note this, we put a semicolon. One way to note it is we put a semicolon and we write a delta H out here. It's called enthalpy. Subscript reaction, and I have a little circle up here, and that refers to standard condition, thermodynamic conditions, 25 degrees C and 1 atmosphere. Right here. And this, of course, would be for the entire reaction, and that is, and I'll put it down here, a minus 91.8 kilojoules for this reaction. It should go out here on the end. And that's the energy that's taking place, the change of energy is taking place. Now notice how I put a negative here. That's indication of an exothermic reaction. It indicates that 91.8 kilojoules of energy is lost from that reaction. Like that. Now, this, what I've written here, is separating the energy number from the reaction body, but it can be written in a second format, which includes the energy number within the body of the equation like this. I can write 3H2 gas plus N2 gas goes to 2NH3 gas plus 91.8 kilojoules. Notice I put the number on the end of the product side. This is the method of indicating that it is an exothermic reaction if the energy number on the product side and included in the reaction, because what you'll see in the next example is an endothermic will take that number and put it on the reactant side. It'll say A plus B plus energy number goes to products. And so the fact that it is on the product side here and it should be an intuitive signal that says, okay, this is an exothermic reaction. It's giving off energy. So those are, I forgot to title it, exothermic. Okay, endothermic. Reactions. One that's commonly understood intuitively for our existence is evaporation of water, or formation of boiling of water. It pushes the water from the liquid state into the gas state. And this requires input of energy into the water to make it go into the steam phase. So we write this H2O as a liquid goes to H2O as a gas phase, and semicolon delta H of reaction under standard state is 44 kilojoules. Now, it does not have a signage in terms of plus or minus. It's not required. The plus is not required. But the fact that it does not indicates it's a positive number. And as such, this is endothermic. Like that. Now, as I mentioned a moment ago, to write this endothermic reaction as with its energy number incorporated into the equation, we want to put it on the reactant side. And this is a commonly used procedure or notation, and shows the number on the left, H2O, as a gas. So placing the energy number on the reactant side indicates endothermic. Now, you never put negatives in the body of the reaction notations. See here in the first example with the production of ammonia, it was exothermic, like that, but when we incorporated it into the equation, we said plus 91. What says it's a loss of energy is the fact that we placed it on the product side. So that's the notation you need to check mark in your notes to be sure you understand. When you see our equation, it's got the energy number posted within the body of the equation. Okay, that energy number is on the product side, so it's exothermic reaction. So, and then there may be other questions in the problems that you deal with that will depend on recognizing exothermic and endothermic from whatever symbology is. So we need to work problems, is what it is. Now, let's start with the equation 3H2 as a gas plus N2 as a gas goes to 2NH3 as a gas, and delta H of the reaction, as we've seen, is a minus 91.8 kilojoules. So that's what we're given, like that. So this is, for all practical purposes, the standard equation. What do we know about the standard equation? Without anything else being written, what is its pressure temperature conditions? Remember? 0 and 1 atmosphere. Everybody remember that? Okay. So the conditions are 0 degrees Celsius and 1 ATM. So that's essentially the standard equation that we're working with. Also, in this, the standard equation, the second element of the standard equation is it's the smallest whole number ratio in the coefficients. If you have fractions in there, which is legal, you can do that. It's not essential, not in the truest definition, a standard equation. So what we're looking at is the lowest whole number ratio of coefficients. And balanced reaction, I should say. Okay, what else do we know about the standard equation in here? What can we say about what we can calculate from it in terms of moles? Well, if I have 3 moles of hydrogen, how much nitrogen will I need? How many? 1 mole. Everybody okay on that? If I have 3 moles of hydrogen, how much ammonia will I expect to be producing? if I have an excess of nitrogen? It says 2. Okay? Well, this is, the coefficients are proportional in yield. In matter yield, how much mass in mass yield? I put mass, sounds better. In mass yield. So, and then we can convert it to moles by multiplying by formula weight grams if we want to go to mass numbers. Okay. The same issue applies once you have your equation to the energy numbers. These values, the coefficient values, are proportional to the energy number. Now, assuming hydrogen is the limiting reagent and we got an excess of nitrogen, when we react 3 moles of hydrogen and an excess of nitrogen, we're always going to kick out 91.8 kilojoules of energy. If I double that to 6 moles of hydrogen and excess of nitrogen, I'm going to get 2 times minus 91.8 kilojoules. So that's what I'm saying. While even the coefficients are proportional, the energy numbers are also proportional in this. So energy numbers associated with a specific equation are proportional to coefficients of standard equation. Okay. Okay. Typically, the problem will give you the equation, the balanced equation, but if it doesn't, you should be able to write one at this point in your education in here. So, what are we given? We're given 2 kilograms and an excess of hydrogen, 2 kilograms of molecular nitrogen, and an excess of hydrogen gas, okay? So, the question is, how much energy will be generated in this process? Well, if we know that this is the limiting reagent right here, it's the moles of nitrogen will determine how much energy. Well, it says how much energy comes from this is 1 mole will produce 91.8. So if we convert this to moles, that'd be 2 over 28 grams per mole. 2,000 grams, because 2 kilograms is 2,000 grams. And so, giving us 71.4 moles. So, if one will generate 91.8, how much will 71.4 generate? 71.4 times the 91.8. So, this would be 71.4 moles times 91.8 kilojoules, well, for the reaction in here per mole of, per 2 moles actually. 2 moles, I should have reduced it. So we got 91.8, so moles. That, I don't want that to confuse you, okay? Because this is dependent on whatever this is. 1 generates 91.8, okay? Yeah, we have 2 moles of ammonia yield. This is actually 2 moles of this will produce that. Half of that is for one mole. But the energy values are relative to the limiting reagent, so this is not necessary. So 71.4 moles is what we have, and that's because of this is a 1-to-1 ratio. It's not multiples. Then whatever that comes out to be is the energy number. I didn't mean to confuse you there. I got 6554.52 kilojoules out of that. And looking, since we have 1 sig fig in the data stream, then we'll say 7,000 kilojoules is the appropriate answer, where 1 sig fig will suffice. Say you're given the following combustion reaction, and it's all gas phase. Let's see. Okay, in this we look at the equation. 1 mole C3H8 will give us exothermic 2043 kilojoules of energy. So the question is, how many grams, this is what they're asking for, it will give us 369 kilojoules of energy. Now, the rule is work it in moles and then convert to grams when you finish this. Well, this is a nice ratio and proportion. 1 mole gives this much, X gives you 369. So we 1 over X is equal to a minus 2043 over a minus 369. This gives us X to equal 369 over 2043, and that'll be in moles of the C3H8. Of course, that's 0.1806. Okay, and then the grams, of course, would be times the formula weight, 3644 grams per mole. And so we get 7.97 7.94713, then on out to some 7 or 8 decimal places by the calculator. Now, what governs the sig figs in this? It's the data. How many sig figs in that? 3. So this needs to be in 3 sig figs, so that would be 7.95 grams would be the appropriate answer for that problem. So this is a better illustration of how these proportionalities will work. And you can hear they're calculating mass, and then the first one we calculated how much energy would be produced when you reduce the mass to some other number. Okay, this is not that difficult, but it skews the mind a little bit and what they're asking for versus what's given. You have nitrous oxide reacting with oxygen to produce nitrogen, should be dioxide, misfire on that one. Yeah, NO2. Yeah, it should be NO2. And you had 114 kilojoules. What's the energy change per gram of nitric oxide? Delta H, energy change per gram of nitrous oxide. So you want to reduce it to energy per gram. Now we can calculate energy per mole, but then we need to convert the energy moles into, let me show you, it's easier to show you than try to explain it in this context. All right, what is the equation showing us? 2 moles of NO yields exothermic 114 kilojoules of energy, right? Okay, so this is the same as times 16 and 14 is 30. Times 30, so this is the same thing as saying 60 grams of NO will yield a minus 114 kilojoules. Now, what they want to do is get this per gram. So, what is the energy change for 1 gram of NO over here? So that's one way to set it up. So you have 60 over 1 equals a minus 114 over X, and you have X equals to a minus 114 over 60 kilojoules per gram. See, this is in grams, kilojoules, and all you're doing is normalizing. If you're not familiar with the terminology of normalizing, what this means is convert the denominator to 1. And that's basically what we're doing, dividing 60 into 114, and so whatever that comes out to be, that's 1.9 kilojoules negative per gram of NO in the process. So it's a matter of perspective here, but the solution sets usually work the same way by proportionalities. Pretty straight stuff. Okay, so if we're given 48.1 grams, we need the moles of ammonia gas, and that's 48.1 grams, 17 grams per mole. .83 mole. So So looking at the equation, and we're assuming an excess of the oxygen, so we have 2.83 mole ammonia will give us exothermic 1267 kilojoules. Well, what will 2.8, excuse me, my bad, 4 moles. 4 moles will give us this, 2.83 mole ammonia will give us X, and that's all it is to it. So once you see these patterns, you really hadn't got a significant problem. Now, mixing it up in other kinds of problems, it can get involved. So we have 4 over 2.83 equals 1267 over X, and solving for X, this is a 2.83 minus 1267 divided by 4, and that's going to come out in kilojoules. I got 896.40 kilojoules, which based on 3 sig figs, we should have negative 896 kilojoules as the appropriate answer in that. Okay. It's not as bad as it looks, and that I'll show you one little issue that you have to deal with. Oh, wait a minute. And we'll go over this when we get back to 31.8 degrees. There. Okay. Energy is equal to Q equals MC delta T. Then M is mass of the limiting reagent out of the reaction. C is specific heat, which is a constant given, 4.184 joules per degree C. And delta T, of course, is temperature change. And in this case is 31.8 minus 25 degrees C. .8 degrees. That's your change. So all we have to do is determine what the mass is, and we'll have it in joules associated with the reaction. Now, the limiting reagent is going to be the HCl up here. And what you're seeing is a solution phase data. So how do I convert solution phase data into moles? Anybody remember that one? What's the definition of molarity? Moles per liter. So molarity times volume in liters is moles. So if I need moles of the HCl, that'd be molarity times volume in liters, which equals 1.2 molar times 0.033 liters. Molarity times volume so we have 0.0396 mole of the HCl. HCl is 36 grams per mole. So we multiply that by 36 grams per mole, and that's 1.426 grams. So we have 1.426 grams up here, grams from our problem right here. So 33 milliliters of 1.2 molar HCl, that's a solution, which will contain 1.426 grams of HCl, like that. So I have all of the data that I need to calculate the energy of this being the limiting reagent. Okay, so that would be Q equals MC delta T would be 1.426 grams, would be this one. C is 4.184 joules per gram here, and then your temperature change was 6.8 degrees C, right there. Oh, this also has degrees C in the, it's joules per gram degrees C. That's right, I forgot that. So grams drop out, Celsius drops out, and you're left only with joules here. So multiplying those together will give you the heat generated by that quantity that we had up here. 33 milliliters of 1.2 molar HCl will generate this much heat, which is 1.426 grams will generate this much heat. So 1.46 times 4.184 times 6.8 equals, I got 40.57 joules for 1.426 grams of HCl. Now, the problem asks you to convert this to molar heat of reaction. What does that mean? So molar heat of reaction is normalizing this energy change with respect to per mole. And this number, 40.57 joules, is per 1.426 grams. So what we've calculated, Q, is 40.57 joules per 1.426 grams right here. So if I want to get that joules per mole, I have to convert this 1.426 grams into moles. I think we did that earlier. So that's 1.426 divided by 36, and that's equal to 40.57 joules over 0.0396 mole. And then you divide that number into 40.6, and we have 1025 joules, or 1.025 kilojoules if divided out by 1,000. So the problems are still proportional and related to equations, but you need to learn about normalization. Normalized to joules per mole. See this, when you divide this out, it gives you this number per mole. It's really per mole, per 1 mole. So it is, people don't report kilojoules per 0.03496. Everybody would convert this to the joules. Now, is it exothermic or endothermic? That's one little trick here. What you made is you took a certain amount of acid and a certain amount of base, You poured them together and you've got a thermometer in there. And what you observed is a 6.8 degrees C rise in temperature. So what are you measuring here? Now this is important, guys, to understanding the physics of what we're doing. You got a thermometer in a liquid. Well, your reaction's over here. That is the system. But the liquid, the thermometer, the beaker, the air, and everything around it is surroundings. So what are you looking at? You're looking at the surroundings gaining 6.8 or increasing 6.8 degrees Celsius. That's what this means. So if that is gaining energy in the surroundings, what is the system doing? Is it losing or gaining? What I told you earlier is it's always opposite, whatever the surroundings is doing. System is exothermic because the temperature is not going to go up in the surroundings unless it gets some heat from somewhere. And the only place to get it is from where? The reaction. So that's the idea why I went through the system surrounding and heat flow and stuff, so that you have that perspective of what's going on. And so that's a good example of that. Okay, go ahead and take about 15 minutes and come on back. I've got to do a couple other things here in this, and then we'll call it a day. I'll see if I can pull up some worksheets for you. Thank you, sir. We've just worked some of these like this. I'll work a couple of these just to kind of get you started. And now I'll encourage you to work as many as you think you need to work in order to understand the concepts, because they'll come back to you, of course, on the big exams. All right, so let's start with the first one in here and see what we can come up with. They've detached the number quite a bit of space between it. But how much heat will be released when 6.44 grams of sulfur reacts with an excess of O2, according to the following reaction? So this is worksheets. So you're given a 2 sulfurs plus 3 molecular oxygens generating 2 SO3s, and delta H of the reaction is given to be a minus 791.4 kilojoules. And in this, you're given 6.44 grams of sulfur. From the periodic table, you'll find the sulfurs 32 grams per mole. So calculating the moles from this, we have 0.2013 mole of sulfur, and of course it notes an excess of O2. So the question is, how much energy will be generated in this reaction from the reaction of 0.2013 mole? Yeah, so that is a 2 to minus 791.4 is equal to 0.2013 to x. And solving for x, we have 0.2013 minus 791.4 over 2, and comes out in kilojoules. I get minus 79.6 kilojoules sig figs, because we have 3 sig figs in the data given. Now remember, don't use conversion factors for your significant figures or constant values. Always from the data. And remember, sig figs are used to express numbers in a practical format and are typically related to laboratory exercises. But it is good to know how to convert these into appropriate values. Okay, this is just the equation written down with this energy number. It says how much heat will be released when 4.77 grams of ethanol, so we've got 4.77 grams of ethanol reacts with an excess of O2. And so our energy number is what we're looking for. Well, here's 1 will give you minus 1366.7 kilojoules. Convert that to moles will give you X. And so that will be the simplest approach. Well, this is 12, 12, 24, 34, 41, 43, 45, 46 grams per mole for the moles of ethanol. Check me on that formula weight. I get 0.1037 mole, and so we're looking at that question mark right there. So it's 1 will give you a minus 1366.7, then 0.1037 will give you X. So you can set it up that way. And X is equal to 0.1037 times a minus 1366.7. It's all going to come out in kilojoules anyway. So 1366.7 equals, I get 141 kilojoules exothermic. 72 kilojoules by the calculator. And we're given 3 sig figs, so this would go to 142 kilojoules, appropriate answer. Everybody kind of see where we are when this, so regardless of where it comes from, you can get it to moles and relate the ratios to the energy numbers. You can solve most of these problems that are equation related. Okay. All right, y'all apply the next view. I'm going to do Hess's law at the end of everything because that gets real gnarly, and right now I don't feel like battling through that. Okay, this section is referred to as energy change and phase transitions. And what phase transitions mean is going from solid to liquid, liquid to gas, and then back down, liquid back, gas to liquid, and then liquid to a solid. So there are energy change considerations in the process. The way I teach this is I teach you first what we call the heating curve of water and express how that is applied to the equations of interest. And then we go into these complicated problems, and I don't think they're all that complicated, but once you see this heating curve of water, I think you'll be a little more adaptable to the problems. So, start this, we want to look at the heating please sketch that on your notepad. Okay, there is the problem we're going to. Okay, slope, slope, slopes. Each of the slopes are warming of the pure condensed phase, pure solid, pure liquid, pure gas. The horizontal lines are two phases in contact, a melting solid liquid interface, and this is a liquid gas interface, like that. So when answering a problem like the one I've listed here, how much energy, total energy is required to go from a, say, minus 10 degrees Celsius to 110 degrees Celsius, you have to do 1, 2, 3, 4, 5 calculations. 1, 2, 3, 4, and 5. Now, what simplifies this is knowing which equations to use in each of the regions that we're going to calculate. If you're working with temperature change regions, and the problem will clearly indicate temperature change, you will have this equation. Q equals MC delta T. And I worked one a minute ago with it. M is mass in grams, C is specific heat. You can have it in calories per gram degree Celsius or kilojoules in gram degree Celsius. And temperature is in degrees Celsius. You don't have to convert to Kelvin in this type of problem. Now, if you're working with the horizontal lines where phase change is taking place, the equation you will use for those regions is Q equals M delta H sub T, or transition constant. So each one of these has a constant associated with it, like they call the heat of fusion. It's 80 calories per gram of water, of ice. Evaporation is 540 calories. Now those will be given to you on the problem, and within the problem, so you don't have to look those up. Same way with the C value. C is specific heat. Specific heat is different for each slope region, and the ice is 0.5 calories per gram, and liquid is 1 calorie per gram, and gas is 0.48 calorie per gram. Now, I've done this enough that I can remember those, but you will be given the C values, the specific heat values, and the delta H transition values, and we'll see those pop out as I go through working each region. Now, you're going to start out your first calculation if you see a slope going to 0 degrees Celsius. It will not melt until the ice reaches the melting point. So you're starting in the problem with a block of ice, 10 grams of ice at minus 10 degrees. So energy goes in from left to right and heats it to 0 degrees. Once the block of ice reaches 0 degrees, then two phases will occur. You have the melting taking place, and the temperature will remain at 0 degrees until you reach all of the ice is melted, and now you're in a pure liquid state. And then you move into this slope line right here, and you have a heating of the liquid. And same way, once you get to the boiling point, then the temperature of the liquid gas interface will remain constant until everything's converted to steam. Then once it's all steam, then you can heat it to the final temperature. That should be 100 degrees C right there. So we're either going to be using Q equals MC delta T or Q equals M delta H of the transition times the transition constant. So one of the things that you should note here is that when you're asking about a problem in calorimetry, that's what this is, if it has a temperature change, you simply use this equation. If it's talking about a phase change, melting or evaporation, you'll use the second equation over here. So the first region we're talking about going from a minus 10 to a 0 degrees, which is a change in temperature, right? So we'll use Q1 equals MC delta T. And so according to the data given, you have 10 grams of ice. Its specific heat is 0.50, I'm going to use calories per gram degrees C, and it's going through a temperature change of 10 degrees C. It's warming from minus 10 to 0. Well, this gives us 50 calories for that first region. So this one would be 50 calories right here. Okay, now we need to get the second region in this problem. Now that's a flat line on the curve, Q2, and so we have no temperature change in the melting process, so we'll use M delta H of transition. Well, the transition constant for this is delta HF, called heat of fusion. That's your melting constant. And so we have 10 grams, and you'll be given 80 calories per gram. And so that is 800 calories for that second region, the flat line in your curve. So this is 800 calories for that one. Now we move into warming of the water that has been melted from the ice, and so that's a temperature change region. So we will use the MC delta T equation for region 3 and call it Q3, and that'll be an MC delta T, which is again 10 grams of water now. Its specific heat of water is 1 calorie per gram degree C, and it's going through 100 degrees C transition and are heating. C's drop out, grams drop out, and we're left with 1,000 calories needed to heat from 0 degrees to 100 degrees. The fourth region is evaporation, and so we see it's a horizontal line. This is 1,000 calories. This one, since it's horizontal, two phases in contact, we'll use the M delta H transition equation. Q4 is M delta H, and it's titled delta H of V, vaporization. It's the heat of vaporization. And so that would be 10 grams of liquid water being vaporized into the vapor state, and the constant given, 540 calories per gram, and so that's 5,400 calories for the evaporation of the 10 grams of water. So this is 5,400 calories. And so the last one in here is warming of the steam from 100 to 110, which is 10 degree increase. So it's the temperature change, so we use the first equation, MC delta T. So region 5 is Q5, MC delta T, 10 grams of steam now, 0.48 calories, that'll be given, gram degree C, times 10 degrees C, and of course that's 48 calories when you calculate it. Celsius drops out, grams drop out, and we're left with calories. Now the total, Q total, is the sum of all the individual Q values. Q1 plus Q2 plus Q3 plus Q4 plus Q5 is equal to whatever that comes out to be. I think it's 76 something. Okay, that adds to 7298 calories, and if you need to go to joules for whatever reason, times 4.184 joules per calorie, and that gives you 30,534. Joules. All right, this is kind of a standard problem that I give in introducing the concepts and worksheets in calorimetry, because I'm not going to give you a problem like this on exam day. What I'll give you is fragments of this. In other words, you start out with ice water and then ask how much energy is involved in getting it to 25 degrees, from 0 to 25 degrees. And so you'll see a temperature change in the problem. So it really boils down to what equation do I apply for this problem. And so you read the problem and make your decision about the equation, and then you apply it. This worksheet kind of close by in your stack, and we'll run through some of these and see that. Everybody find it? Just change the state in there. Okay. All right, read this first one. It says, how many joules are required to heat 250 grams of liquid water from 0 to 100 degrees? Now, is that a temperature change problem?
Yes.
Which equation are you going to use? MC delta T. Okay, that's all it is. All right, look at the next one. How many joules are required to melt 100 grams of water? How many joules are required to boil 150 grams of water? Is there a temperature change in melting and boiling?
Yes.
No, there's no temperature changes. When phase change occurs, no temperature change is present. See, phase change, this is melting, and this one is boiling. So in this, you don't see a temperature change. In these, so you would be using this M delta HT. Is everybody kind of on that? Everybody good? It's all it is to it, guys. So in test day, or as you go going through these, don't beat yourself up in terms of what they're trying to achieve here in the problem. You decide on whether it's temperature change or not temperature change, and apply that to the equations. And there are only two equations, one with the temperature change and one without. And so the problem usually, if you use the right units and stuff, the problem will solve itself. Okay, number one, it simply says, how many joules, well, it asks for joules, I answer in kilojoules, just times 1,000. How many joules are required to heat 250 grams of liquid water from 0 to 100 degrees? Well, we just said that's a temperature change problem, so I'm going to use Q equals MC delta T, where M is 250 grams given, C will be given. If you want to do it in joules, it's 4.184 joules per gram degree C, or if you want to do it in calories, it's 1.000 calories per gram degree C, and you can convert back and forth as you wish. I think the data they give you at the top is in joules per gram degree C, but it really doesn't matter in most cases. Depends on the problem they're asking. Delta T is a transition from 0 degrees C to 100 degrees C, so this would give you a delta T equal 100 degrees C. And so it's just a plug and chug now. So Q equals 250 grams times 4.184, which they in joules, or 1 calorie, grams degrees C, times 100 degrees C. Celsius drops out, grams drop out, and you're left only in joules. That's 25,000 times whatever 4.184 is. What did I get? 100,000. See if I get the same answer, 250 times 4.184 times 100. So that gives me 104,600 joules, which is equal, divided by 1,000, 104.6 kilojoules. And using this as 250, actually, if you remember the sig fig video, it only has 2 sig figs. So in reality, this would be 105. But you only have 2 sig figs, so that'd be 110 kilojoules, because that would change that to a 5, and 5 would change that to a 1. So this is 2 sig figs. We'll leave it at that. You don't have to worry about that, because just look at the answer choices. It'll tell you what degree of accuracy you'll need. 2. And you'll be given 80 calories per gram, okay, as equal to the delta H fusion for melting of water. So since this is a phase change, melting, will temperature change be involved? Will it be involved? No. It'd be the Q equals M delta H, dot delta H of fusion this time. And M is 100 grams, and we're given the 80 calories per gram. That drops out, and so you have 8,000 calories. And if you need it in joules, multiply by 4.184 joules per calorie. And that's 33,472. Or 33.5 kilojoules, 3 sig figs in that. So we went that far. Okay. So we want to now find this worksheet, this calorimetry worksheet. Starts off a swimming pool, given certain volumes, and oh no, I don't think I'll work. The sum of all energy changes that are taking place in the problem will be zero. Heat loss equals heat gain, as some people will present it. Now, what this means is you have to read the problem and determine what energy factors are involved. There may be melting and then warming and then melting again, and it stops. So you have 3 energy factors involved in something like this. Let's look at that second problem in here and just kind of whittle through that to see how it applies to this formula. A 75 gram sample of metal is placed in boiling water until it is 100 degrees Celsius. So you have metal, mass of the metal equals 75 grams at 100 degrees Celsius. A calorimeter contains 100 grams of water at 24.4. So mass of calorimeter of water, let's just put water in there, is 100 grams at 24.4 degrees C. Okay, now what this ultimately involves is dropping the metal into the water and asking, well, what's the final temperature in the middle? Okay, and you have to decide whether melting or phase changes or warming or cooling, whatever is involved in the process. So picture's worth 1,000 words, as they say in math, and I agree with them. So what you're going to do is you're going to drop this metal in here, and so the metal loses energy and temperature decreases. The water gains energy from the metal, and temperature increases. And they're going to meet in the middle at what we call a thermodynamic equilibrium temperature. I'll write it down. And that's what we're looking for in solution to this problem. Now, as you read this problem, see the final calorimeter proves to be a perfect insulator. See the final temperature of the metal and water in the calorimeter is 34.9 degrees Celsius. And they want to know what the specific heat of the metal is, given the specific heat of the water. Okay? So that's kind of a graphic layout of the problem. And does everybody understand the problem itself and what we're looking for? We're looking for specific heat, and we're looking to get that number from adding a hot metal to cold water. And they're going to wind up in the middle. Temperature final, I'm going to call it TF, 34.9 degrees C. Now, to work a problem like this, what's happening? This is cooling to a lower temperature, and the water is increasing to a higher temperature, right? So are those temperature change problems? Absolutely. Which equation are you going to use? MC delta T, right. Now, since there's no melting involved, you won't have to use the M delta H equation at all. Just the MC delta T. And we'll do one with melting included. Okay, so the sum of all your energy changes must equal 0. Well, what are your energy changes? Let's say Q is the metal plus the Q of the water has to equal 0, regardless if it was a gain or loss of energy. That's why I like this approach, because you just add up the energy changes and let the math take you to where you need to be. Now, since these Q's refer to the changes, phase changes, or temperature change in this case, then we have this equation right here to be MC delta T of the metal plus the MC delta T of the water. All that equals 0. See what I just did? So I identified in the problem itself what kind of changes in heat flow is involved. In this case, it's warming and cooling and a temperature change. If there was a melting process involved, I would stuff that one in there as a M delta H of whatever. And they'd have to give us the delta H. Okay, I'm going to have to hide some of this stuff. All right, the metal was 75 grams, so you bring in 75 grams of metal. The problem's objective is the specific heat of the metal. And I'll just C sub M. The temperature change is the final minus initial, 34.9 minus 100 degrees C, like that. So there is your, don't worry about the signage. If you're using this sum of Q equals 0, the signage will take care of itself at the end of the problem. You won't have to worry about it. And I'll show you. Okay, so here is the metal plus the MC delta T of the water, and we have, how much water was it? 100 grams, okay. 100 grams of water is 4.184 joules per gram degree C. Times the change in temperature, that's going from 100 down to 34, so you would have 34, let's see, final would be, let's see, initial was 24.4, right. Initial, final minus initial is what I should do. 30, come on. 34.4 minus 24.4, and that's degrees C. All that goes right in there, and everybody still equals 0 in that. So we're looking for C in this. Now, if you set this up like this, I guarantee you that the units of the final answer will be in joules per gram degree C. That's the specific heat, I assure you. Now, don't, minimize what I just said, because what I've said is if you set it up right, then that's going to be correct. So what I'm trying to do is tell you, drop all the units out, and let's get that change. Well, I put it all in there, 34.9 minus 100 right there, and that's the metal, plus 100 times 4.184, and then 34.4 minus 24.4, all equals 0, and that goes up there and there. So what I'm showing you here is a simplification. Makes the math a little bit easier. Anyway. All right. So we begin to simplify and solve for C. That's all we're going to do. And so, this is 75 times C times a minus 65.1 right here, plus 100. That's 34 to 24, that's 10, 1,000 times 4.184, so that's 4184 out of that, which equals 0. Y'all buy that? Okay. So let's get the 65 times 75. 65.1 times 75 equals a minus 4882.5 times C equals plus 4184, all equals 0. Now I'll transpose this to the right side or vice versa, but it all comes out 4882.5 times C equals 4184. Solving for C is 4184 over 4882.5, and that's going to come out in joules per gram degree C. So it's just a matter of substituting and working through your algebra. You have to be very cautious about making your entries in the equations so you don't miss the signage or make a mistake in that. By using this, always in the temperature thing, final minus initial. So you have to keep those in mind. Now some people will teach heat lost equals heat gain, and in that case you have to swap the signage. And that complicates, and many students struggle with that. But this, use always second minus the first, and the signage will take care of itself in the math. So, and so 8.857, 0.57 joules per gram degree C. So that's our objective. So you see, it's kind of a combination of the two formulas, and you have to decide from the problem what's happening in the heat flow of the two. Now, the next problem is a very classic, and I do give this one like this on exam. Okay, we're given mass of water is equal to 30 grams at 280 Kelvin. Is mixed with, let's call this mass water 1. Mass H2O, mass 2 is 50 grams. at 330 Kelvin. Calculate the final temperature of the mixture, assuming no loss of heat to the surroundings. Heat gains is equal to heat loss. Well, we're going to do it by the sum of energy changes equals 0. So what does this all involve? It means you've got 30 grams at 280 Kelvin plus 50 grams at 330 Kelvin is going to give you 80 gram mix at whatever the final temperature is. You're pouring them together. So what's going to happen? You have one at the lower temperature is going to go to the middle temperature, so you're going to wind up in the middle somewhere between these two, right? Would that make sense? So if you're going to wind up in the middle, what is this one going to do? Increase in temperature or decrease? This is increasing temperature. So that is gaining energy. Well, this one over here is going from 330 down to whatever that middle temperature is, and that's decreasing temperature. So that's going to go in heat loss, and you're going to wind up somewhere in the middle of that. So now that's needed. You need to go through that mental process in order to put together your problem. So all you have is a temperature change problem. So this would be MC delta T for 1, and this will be an MC delta T for change 2. Put those together and set them equal to 0. That's all it is. Make sense? So you just identified this one, and you identified this one, and you mixed them together to get this. But the changes are all going to add to 0. So, what are our masses? Well, number 1 is 30 grams, and the water is still 1 calorie. I'm going to do it in calories per gram degrees C. And we're going from 330. We're going T final. I'm going to make that the unknown. T final minus 280 Kelvin. And you can do it in Celsius. I better do it in Celsius. Each one of these. That's 7 degrees. And then 330 is 57 degrees C. Okay, so in the first one, the low temperature is increasing from 7 degrees C to T final. And then you're going to add that to 50 grams of water, still 1 calorie per gram degree C, and it's going to T final minus 57 degrees C, and that equals 0 in there. Now all you got to do is solve for the TF in this problem. Well, what's TF going to be in degrees C? So I'm going to drop out all the units, and I'll go 30 times 1 TF minus 7 plus, and we'll make that number 1, and that's 50 times 1 times TF minus 57, and that's equal to 0. Now, wouldn't that be easier to solve? Isn't that easier? Maybe. So we have 30 TF minus 210, whatever that is. So put that here plus, and then 50 TF minus 50 times 57. I don't know what that is. 2850. So this 1 and 2, and all that's equal to 0. Now remove the parentheses. I put them in there for emphasis on the problem. So we have 30 TF minus 210 plus 50 TF minus 2850. all equals 0. And so 2850 plus 210 equals 3060. So 5, 6, 7, 80 TF minus 3060 equals 0. And so that's 80 TF equals 3060. And your final temperature is 3060 over 80 degrees Celsius. And it's 38 degrees C. Well, now when you get your answer, be sure it's between the two temperatures. Because that's where it's going to, if it's above or below, you need to go back and check your calculations. Okay? So in that case, let's see if we got it. That next page over, I think, is out of sequence. That goes with the heat of reactions at the beginning. Well, I was looking for one that had a phase change in it. I may have to make that one up. Let me see. Yeah, it looks like I'm going to have to. This involves the same issue in that you are making ice water. That's what you're doing. And so you have 50 grams of water in which you are adding 10 grams of ice into 50 grams of water, and this is at 25 degrees C. Now, the heat changes that take place in here, for the water, it's going to be going down from 25 to wherever the ice is, and that's 0. You assume that's 0 degrees right there. So that's going to be a decreasing temperature for the ice, for the water itself. But the ice is the thing that you have to pay attention to. There are two changes here: melting of ice and warming of ice water. That's what I. So when you write your equations out for your Q's, Q1, Q2, Q3, you got three changes. You've got, of course, warming of the water, and you've got a Q for warming of the ice water, and then you've got a Q for melting. Well, that's a phase change, so you will use Q equals M delta H of fusion in there. This one is an MC delta T to the final temperature from 0 degrees Celsius to T final. Well, this one is 25 degrees Celsius to T final, whatever it's doing. So when you write your sum of your heat changes, you have to take into account, well, we got to melt 10 grams of ice. So that's an M delta H of fusion for the ice. Plus, then you've got to warm the ice water. It's an MC delta T, I water. You have to warm it, plus an MC delta T, where you're cooling the water, the tap water. Okay, and so now you put in your data and solve for the unknown. You've got 10 grams of ice, 80 calories per gram, plus 10 grams of ice water now, 1 calorie per gram degrees C, and you're going from 0 degrees final to final temperature, that's TF, minus 0 degrees C. That's the second one, plus this one. That's your melting, that's your warming of ice water, melting. And then you have 50 grams of water that you're cooling, that's 1 calorie per gram degrees C, and it's going to a T final from 25 degrees Celsius is where it started. And so all of that is equal to 0. And so in this case, you only have one unknown. Drop all the units out, simplify, and solve for TF. It'll tell you where the final temperature will be in making your ice water. So I try to give you an example of each one of the types, and I will be giving you something that's just identifying a temperature change or phase change, a single problem, to combinations of what's going on in some of these. Now next time we're going to go into Hess's law and standard heats of formation, which I mentioned in the beginning of the course. Those things you find in the tables in the back of the book. And so with that, I'm going to say, okay, that's all I've got today.